All right, today we're talking about scientific notation. The reason why we do scientific notation after our two properties, multiplying and dividing exponents, is we actually get to use those in the operations between scientific notation expressions. So first of all, we need a little review on what scientific notation is. And really, it's just a number written in this form, a times 10 to the nth power. And there's a couple rules to go along with that. A has to be in between 1 and 10, and it can be 1, but it can't be 10. And we'll talk about why that is. And n has to be an integer. Okay, so that 10 to the nth power, the n has to be basically a positive or negative whole number. Okay, so let's just look at a quick example here. And usually we use scientific notation to represent big numbers and very, very small numbers. For example, like the distance around the Earth, or the mass of the Earth, or looking at all the scientific things that you look under a microscope. Those are very small figures. Okay, so if I want to represent the number, let's just say 8,760,000. I want to represent this number in scientific notation. If we take a look, it says a times 10 to the nth power. That a has to be between 1 and 10, basically. So what it's saying is, I'm going to put a decimal in this number, and really, this decimal, so for a, wherever I put this decimal, there can only be one digit to the left of that decimal, right? Because my number is going to be between 1 and basically like 9.999, right? It can't be bigger than 10. So if I look in this number, 8,760,000, I want to put my decimal right in between the 8 and the 7, because then I'm only going to have one digit left of the decimal. Okay, if I put it anywhere else, I'll have more digits left of the decimal. So that's my first step. I put my decimal right in between, right after that 8. So 8.76, and then we have a rule that if there's unneeded zeros, we just get rid of them. So I don't write any of these unneeded zeros anymore. And then I'm going to write it times 10 to some power. Okay, so to think about what power we write to, we have to look at our number. Well, this 8.76 times 10 to some power is going to represent our big number here, our 8,760,000. Well, when I multiply by powers of 10, if I multiply by 10, it just moves my decimal one spot to the right? Or if I multiply by 10, it adds a 0 to the number. So for example, if I had 8.7 times 10, it just moves my decimal 1 to the right. So I get 87. If I multiply that by 10, now I just add a 0 onto that 87. Okay, so it either moves your decimal to the right or adds zeros. So if I think about it, this 8.76, how many times do I got to move my decimal right to get the number I wanted originally? 8,760,000. Well, 1, 2, 3, add that 0, and then I need 3 more zeros for my hundreds. So really I moved it 1, 2, 3, 4, 5, 6 places, which gives me 10 to the 6th power. Okay, a little confusing right now, but let's take a look at a few more examples. It might help to go from standard form to scientific notation right away. These steps are written on page 416 of your book. I don't think it's very good to try to memorize those steps. If you can just reason why it works the way it works, then you don't have to memorize these steps. And so that's why we want to do it that way. So let's just take a look at an example and see if we can make sense of this. So I got the number 68,700,000,000, and I want to change it into scientific notation. So we got to decide, where do we put our decimal first? Well, remember, I can only have one digit left of the decimal, so I'm going to put it right after the 6. So it becomes 6.87. Well, remember, we drop all those unneeded zeros, times 10 to some power. Well, the 6.87 is going to represent a bigger number, right? A 68 billion. So I got to see how many times my decimal moved. And if we take a look, it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots. 10 spots. So that would be my answer. 6.87 times 10 to the 10th power. That would represent my 68,700,000,000. Well, what would happen if I needed to represent a smaller number? A smaller number. Same type of thing, I got to decide where's my decimal going to go. Well, I can only have one digit left of the decimal, so I'm going to put it right after my 7. So I got 7.25 times 10. Well, let's think about this now. How much did my decimal move here? 1, 2, 3, 4, 5. So is it going to be 10 to the 5th power? If I think about that, that means I'm moving my decimal right, correct? So I would go 7.25, 1, 2, 3, 4, 5. Add my zeros. Well, that's not the number I'm looking for, is it? So instead of saying to the 5th power, how would I go backwards? Instead of multiplying by 10, don't we want to divide by 10? Well, that goes back to our negative exponents. When we have a negative exponent, it's really dividing by 10 instead of multiplying by 10. So instead of saying a positive 5, it'd be 10 to the negative 5th power. 10 to the negative 5th power. And this will make a little more sense when we go from scientific to standard. Okay? So let's take a look at that. Let's go from scientific to standard form. We're probably okay with this first method. 6.49 times 10 to the 5th. I am going to a bigger number, so I just move it to the right. 1, 2, 3, 4, 5 spots. You just take a look at what your exponent is and add your zeros. So we have 649,000. Well, a negative exponent, would it just go the opposite way? We would just go left, right? We're dividing by 10 instead of multiplying by 10, essentially. So I got 1.8, and this time instead of going right, we're going to go left because we want a smaller number. And we go left 3 times. So that negative just tells us go left and move it 3 times, and we just add our zeros in where those spaces are at. 0.0018. And we could put a 0 out front, but we don't really need to. So there's the difference. We can also use this, what I was talking about earlier. We can use our properties of our exponents to solve some arithmetic here. So for example, if I was trying to multiply either very big numbers or very small numbers, it can be overwhelming with all those digits. Well, I took this expression and I wrote it in standard form here. Okay, so I'm going to evaluate this and express the result in both scientific notation and standard form. So first thing, let's get in scientific notation. And if you look, this just says 5 times 10 to the negative 6 times 2.3 times 10 to the 12th. So it's all multiplication, right? And multiplication is associative and commutative. So I can multiply whatever I want first. So would it make sense to multiply my 5 and my 2.3 and then multiply my 10 to the negative 6 and my 10 to the 12th? Right? That's perfectly fine to do that. Because I can multiply whatever I want first. Well, we should all be able to take 5 times 2.3. Our 5 times 3 is 15. Carry the 1 for 11. And it looks like I have 1 decimal place. And we're going to take that times, well, we're going to look back at our exponent properties here. I got the same base. So what do I do with our exponents? We just add them together, correct? So we're going to take 10 to the negative 6 plus 12, which gives us 10 to the 6th. And we are multiplying in between there. Here's our one issue, though. Remember, I can only have 1 digit left of the decimal. So let's rewrite this 11.5 in scientific notation. Well, I want my decimal to move here. So I needed to move 1 over there, right? So 1.15 times 10 to the, well, first power, I believe, right? Because we want that decimal to move 1 to the right to give us 11.5. And I still have this times 10 to the 6th. So we combine those to give us 1.15 times 10 to the 7th, right? Because I got the same base. We just add their exponents. So there it would be in scientific notation. And if I wanted that in standard form, we just move our decimal 7 times to the right. So 1.15, 1, 2, 3, 4, 5, 6, 7. Add our zeros and put in our commas. So 11,500,000 would be our two answers. Okay, I can do the same thing with division. I can split this up. Since it's multiplication, right, 4.5 times 10 to the 8th and 1.5 times 10 to the 10th, I can split that up and do it separately. I can divide these two separately and then divide these two separately and multiply. So let's start it out. 4.5 divided by 1.5, really 45 divided by 15 to give us 3. And we're going to multiply, well, 10 to the 8th divided by 10 to the 10th. Remember, when I divide, I just subtract their exponents if they have the same base, which they do. They're both 10, and so 8 minus 10, which gives us 10 to the negative 2. So there we go. It's almost in scientific notation. I just got to add my decimal. Well, I already have one digit left for the decimal, so let's just put our 0 behind it, times 10 to the negative 2. So there's scientific notation, and we want it in standard form. Well, it's a negative exponent, so we move it 2 spots to the left now. 1, 2, they give us 0.03, and I can add that 0 in front. I don't have to. And there we go. So there would be our 2 answers. Here's our assignment for tomorrow. If you have any questions, feel free to ask. I'm going to be walking around the room, and we'll get after it.